I am Dr. Rakapan, reader in physics and Amla University. Dear students, today let me talk about the elementary ideas of crystallography in solid state physics. The solids can be broadly classified into two categories. One is crystal and other one is amorphous. The crystals are solids in which the molecules or atoms are arranged in a regular periodic fashion. In amorphous, the atoms and molecules are arranged in a random fashion. The crystals have a peculiar property of directionality. But in the case of amorphous, the solid substances which have isotropic character, which is absent in the case of crystals. The directionality, in the sense, if you take an optical property, the light intensity will be maximum along a particular direction when compared to the other directions. So the light intensity, when you see along the optical axis, it is maximum. That indicates that along that particular direction, the property is reaching its maximum, and in other directions, the property is little bit changed with respect to the optical axis. So this type of property is called anisotropicity. To understand the basic ideas of crystals, let us start with what is lattice. A lattice is a regular periodic arrangement of points in space in which, if you go into the lattice and view the lattice from two different positions, say from R and from R prime, the lattice looks same from both the points. The relationship between the points R and R prime are given by a simple relationship. R prime is equal to R plus T, where T is the translational vector. T is equal to N1A plus N2B plus N3C, where N1, N2, N3 are integers, A, B and C are the primitive vectors or fundamental vectors which forms the adjacent edges of a parallelepiped. A primitive cell is a cell in which the edges of the parallelepipeds used to have atoms at its corners. In the case of non-primitive cells, in addition to the corner atoms, there are atoms at the center of the body or at the center of the face, which are called non-primitive cells. Then, what is a basis? Basis is a basic repeating unit assembly which may be an atom or a molecule or a radical. If you place this basic repeating unit assembly on each and every lattice point, which produces the entire crystal structure. So the crystal structure can be given by a simple relationship, the lattice plus basis is equal to crystal structure. What is a unit cell? A unit cell is a geometrical figure or a small volume element which repeats itself in all the three directions to produce the entire crystal structure. For example, if you take a wall, the wall is made up of bricks, and you just take a small brick. That brick repeats itself in all the three directions along the length, breadth and height, which produces the entire wall. So rather than studying the strength of the wall, it is enough to just study the strength of the brick alone. That will give you the character of the wall. Like that, the entire crystal need not be studied. For studying the crystal characters, it is enough you just study the character of the unit cell alone. So naturally, the crystal unit cell contains all the information about the crystal. The unit cell can be explained using the lattice parameters A, B and C. They are the primitive vectors under the interfacial angles alpha, beta and gamma. The alpha, beta and gamma always represents the angle between the y and z axis, z and x axis and x and y axis respectively. Then, to understand the crystal structure, we should know what is a group and what are the possible symmetry groups, because the symmetry groups characterize a particular crystal structure. What is a group? A group is a collection of elements which obeys a certain set of rules. The symmetric groups can be classified into two categories. One is a point group and another one is a space group. What is a point group? A point group is a collection of symmetry operations which, when applied about a lattice, leaves the lattice invariant. What is a point group and what is a space group? the space group, when you place the point groups at each and every point of the lattice, then there emerges a set of symmetry operations. That symmetry operations forms a group of its own, that is what is called the space group. There are about 32 point groups and about 230 space groups in total. When you view the crystal structure externally, then you can see only the point groups. But when you go into the crystal structure, you can have 230 space groups. Normally, the symmetry elements which we use are the reflections and the rotational symmetrical operations. So in a point group, we have only the rotational and the reflection symmetry operations. So when you place this symmetry operations or the symmetry groups on each and every point, there emerges the symmetry operations in addition to the rotation reflections. Those symmetry operations are the screw axis and glide planes. So these screw axis and glide planes will combine with the rotation and reflection operations, form other set of symmetry groups, and that leads to the rise of 32 point groups to 230 space groups. So it is very difficult to remember or to recollect all these 32 point groups or 230 space groups. So what Brevis has suggested, rather than recollecting all these things and distinguish the crystal structures, it is enough, or you can introduce the concept of the Brevis lattice. What is a Brevis lattice? According to Brevis, the positioning of structureless points in space such that each and every point will have identical surroundings. So based on this concept, Brevis has classified the crystal into two categories. That is, when one two dimension, the crystals can be classified into 5 types, and in the case of 3 dimension, the crystals can be classified into 7 systems and 14 classes. In the case of 2 dimension, the Brevis lattices are square lattice, oblique lattice, hexagonal lattice, primitive rectangle lattice, and centered rectangle lattice. So these 5 types forms the Brevis lattice in 2 dimension. And these 5 Brevis lattices have a unique relationship in the lattice parameters, that is A and B, and the angle between x and y axis, that is gamma. In the case of 3-dimensional Brevis lattices, there are 7 systems and 14 classes. Those 7 systems are cubic, tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral, and hexagonal. In these 7 systems, each and every system has got its unique classes. In the case of cubic, there are 3 types. One is basic primitive unit cell, in which we will have atoms only at the corners, and the body center. In addition to the corner atoms, there are atoms at the center of each unit cell, and in the case of face centered, in addition to the corner atoms, there are atoms at the center of each face. In the case of tetragonal, there are 2 types. One is primitive and other one is body center. And as you know, the primitive, in which the atoms are only at the corners, and in the case of body center, in addition to the corner atoms, there are atoms at the center of each unit cell. In the case of orthorhombic, there are 4 types. They are primitive, body center, face center, and base center. We have already seen what is a primitive, what is a body center, and what is a face center. What is a base centered? A base centered crystal structure is the one in which we have atoms only at the top and the bottom base. The atoms at the center of the top and bottom base is called base centered structure. So in the case of orthorhombic, there are 4 classes. They are, once again I will repeat it, the primitive, body center, face center, and base centered. In the case of monoclinic, there are 2 types. One is primitive and other one is base centered. In all the other 3 categories, that is in triclinic, then hexagonal, and in rhombohedral, they are one apiece. They are all primitive cells or the primitive types. So these are the 14 classes of Brevis lattices. So all the available solids, crystalline solids, have to fall in any one of these 7 systems or the 14 classes. So naturally the Brevis lattice gives the total picture of the crystal structures which are available in the universe. So to understand the basic crystal structures, the reciprocal lattice concept was introduced. What is a reciprocal lattice? We know already what is a lattice, which is nothing but a regular periodic arrangement of atoms in space. The reciprocal lattice is once again the regular periodic arrangement of points in space, but each and every point represents a set of planes. Why should we study reciprocal lattice? Because to understand the X-ray diffraction concept, the reciprocal lattice should be studied, because the X-ray diffraction picture won't give you the regular lattice picture, it will show you only the reciprocal lattice picture. Then what do you mean by reciprocal lattice? So a reciprocal lattice is just representing a set of planes, which means that the crystal contains a series or the sequence of planes in a particular direction, which has got a unique interplanar spacing. So you just choose a set of planes in a particular direction, say the interplanar spacing is d. Then you choose an arbitrary origin and you connect that arbitrary origin to that set of planes through a line. You put a point on the line. By marking a point, that point should be at a distance of 1 over d from the origin. That point is nothing but the reciprocal lattice point. That reciprocal lattice point just represents the set of planes in that particular direction. So the characters and properties of the planes and points are interchangeable. So this reciprocal lattice picture gives you the concrete form of the regular lattice picture. Rather than visualizing the crystal as the interpenetrating planes, it is very easy to visualize it in the reciprocal lattice form, and that is the form which we get in a X-ray diffraction pattern. Based on this reciprocal lattice pattern, Ewald has developed a sphere called Ewald sphere or sphere of reflection, in which the crystal is kept at the center and X-rays are allowed to fall on the crystal. So once the X-rays falls on the crystals, it gets diffracted. By keeping the crystal as center, we can draw a sphere with a radius equal to 1 over the wavelength of the incident radiation. So you just place your camera or a photographic film at the surface of the sphere, then that film will absorb the diffracted beams. Once you start rotating the crystal, then what do you mean by that? That reciprocal lattice inside the crystal is also rotating. So every time when a reciprocal lattice intersects a sphere, then a beam will shoot out of the sphere center, that is from the crystal, and it will impinge on the sphere circumference where we keep our photographic film. So when a crystal is rotating, the reciprocal lattice in that is also assumed to be rotating, and whenever a reciprocal lattice point intersects the sphere, then the beam will shoot out of the sphere center and the points are occluded on the film, and that points are nothing but the reciprocal lattice points. Usually the film is in the form of a sphere, and if you remove the camera and expand it, you can see the lot of dots on both sides of the center of the sphere, where the center is nothing but the beam leaves the sphere when the crystal is absent at the center. So the origin or the exit of the X-ray beam is chosen as the origin, and being that's exit point as origin, the distance from the origin to that reciprocal lattice point will give you the distance d, and the reciprocal of the distance d will give you the interplanar spacing between the planes of the crystal in that particular direction. So this evolved sphere concept is highly helpful in determining the crystal structure. Based on that, the X-ray diffraction technique can be classified into 3 categories. The one is the Auddeyt technique, and second one is the rotating crystal technique, and third one is powder photograph technique. In the case of Auddeyt technique, the single crystal is kept constant in the midst of a beam of X-ray radiations which contains a range of wavelengths. But in the case of rotating crystal method, a crystal is kept at the center, which is rotated in the midst of a monochromatic beam, and in the case of powder photograph method, the crystalline samples are powdered and which is exposed to a set of X-ray radiations. What you can observe in these three techniques is the basic fundamental idea is Bragg's law, 2d sin theta is equal to n lambda, where d is the interplanar spacing, theta is the angle of incidence, and lambda is the wavelength of the incident X-ray radiations. So once you change the theta, we have to keep lambda constant so that the variation of theta with d can be studied. Otherwise, we can keep theta and change the lambda, and the variation of lambda with d can be studied. In all these three techniques, we are using the concept of changing either theta or lambda with respect to d. So these three techniques will give you the reciprocal lattice pictures, which in turn will give you the regular lattice picture. All these three techniques gives you the reciprocal lattice picture, which in turn gives you the regular lattice picture. The next one is the Miller indices. What are Miller indices? We know that the crystals consists of lot of planes in it. Each and every plane has got some intercepts along the x, y and z axis. The intercepts are usually not the numerical parameters, but they are the reciprocals of the numerical parameters. If you take a plane which has got intercepts at A, B and C along x, y and z directions respectively, let me say that A, B and C are 2, 2, 1, then they won't be represented as 2, 2, 1, they are usually represented as 1 by 2, 1 by 2, 1 by 1, or otherwise they can be multiplied by the greatest common denominator, that is 1, 2. That is, we have multiplied all these things by 2 so that we get the Miller indices, that is H, K, L, which are put within the parenthesis. And a set of planes, that is the equidimensional planes, are usually represented within braces, and the Miller indices of a given plane is represented within parenthesis. So these are the basic fundamental ideas of crystallography. So we started with what is a crystal, what is lattice, what is basis, what is a unit cell, what are lattice parameters, what is a group, what are symmetry groups, what are point groups, what are space groups, and what is Bravais lattices, and what are Bravais lattices in 2 dimension and 3 dimension, and what is a reciprocal lattice. Based on reciprocal lattice, how evolved sphere concept has been developed, and then we have seen what is Miller indices. So these are the basic elementary ideas of crystallography from which the crystal structure can be easily understood. Now let us see some important engineering material structures, or the structures of some important engineering materials, or otherwise the closest packings in engineering materials. What are closest packings? The closest packings are nothing but arranging the equidimensional object in space such that the available space is occupied very effectively. There are two ways by which the atoms or the equidimensional objects can be arranged in space. The one is the square lattice pattern, the other one is the triangular or hexagonal lattice in 3-dimensional pattern. What is a square lattice? The square lattice is the one in which the number of equidimensional object about a particular object is 4, but in the case of hexagonal lattice, the number of equidimensional object about a particular object is 6 in the case of 2 dimension and 12 in the case of 3 dimension. So in the closest packings, the effective way of filling the available space is very, very important. The closest packings are usually classified based on the sequence. How many layers are required to complete the entire structure. If only 2 layers are required, then the periodicity is 2, or the rank of the crystal is 2. If the number of layers required to complete the structure is 3, then the periodicity is 3, and if the number of layers required is 4, then the rank of the crystal is 4. For example, if you assume that each and every atom is in the form of small spheres, and they are arranged in a regular periodic fashion in space, and they are positioned at points A, and since they are small spheres, they are touching each other. In between the spheres there are small voids or vacancies which are in the form of triangles. There are two types of triangles. One is the triangle which is pointing downward, and other one is the triangle which is pointing upward. The upward triangles, let me call it as the position B, and the downward triangles, let me call it as position C. Initially we have placed the atoms at the positions A, and the second layer can be placed either at B or at C. For our convenience, let me choose the second layer goes into B, then the sequence will be AB, 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 and the rank of the crystal is 2, and that type of arrangement is what is called as hexagonal closest to packing, or simply it is HCP. If the sequence is in the form of ABC, ABC, that is the first layer is A, and the second layer is B, and the third layer it will go into C rather going into A in the earlier case, then the sequence will be ABC, 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 and the rank of the crystal is 3, and that type of arrangement is what is called as face centered cubic structure, or simply it is FCC. In the case of rank 4, that is given as ABAC, ABAC, and that structure is what is termed as topo structure. We are interested only in this hexagonal closest to packing and face centered cubic structures. So most of the important materials choose either this hexagonal closest to packing or face centered cubic structure. So we are going to see how these hexagonal closest to packing and face centered cubic structures are arranged, or how the atoms are arranged in HCP and FCC. Before going into those structures, there are some rules which governs this closest to packing. To know the rules or to understand the rules, there are three important factors that we should know. One is atomic radius, second one is coordination number, third one is packing density. What is atomic radius? Atomic radius is nothing but half the distance between two nearest neighboring atoms. And what is a coordination number? The coordination number is the number of nearest neighboring atoms around a particular atom. What is packing density or packing fraction? It is the volume occupied by the atoms in a unit cell divided by the volume of the entire unit cell. That is small v divided by capital V, where small v is the volume of the atoms occupying that unit cell, and capital V is the volume of the unit cell. So now let us see what are the rules which governs the closest to packing. There are three rules. The rule number 1 is each and every atom should touch the nearest neighboring atoms, and the distance between those nearest neighboring atoms should be equal to 2r, where r is the atomic radius. And second one is the stacking sequence should be continued throughout the crystal. There should not be any break in the sequence inside the crystal. And the third one is the volume or the amount of vacancies available in the crystal should be less than the atomic diameter which forms that particular crystal. So these are the three basic fundamental rules which governs the closest to packing. So first let me take what is hexagonal closest to packing. In the hexagonal closest to packing, the number of coordination numbers is 12. In the case of hexagonal closest to packing, there are 6 atoms in the same layer, 3 atoms above that and 3 atoms below that, so that the coordination number is 12. If you see that hexagonal closest to packing structure, as you imagine, it is not a simple hexagon with 6 edges. There are 2 hexagons which are connected with each other by straight lines in the z direction. So in the center of those lines, there are 3 atoms exclusively attached only to that hexagonal closest packed structures. So you just see the number of atoms available in that particular unit cell, that is 6 atoms at the edges of the hexagon, Therefore, the total number of atoms at the edges is 6 into 1 by 6 in the top face. In addition to that 1 by 2, there is an atom at the center of the hexagon, that is 1 by 2 plus 1, that is 3 by 2. And in the same, similarly, there is another set of hexagon which is having 3 by 2 atoms and 3 atoms exclusively at the center. So the total number of atoms in the unit cell is 6. 3 by 2 plus 3 by 2 plus 3, that is 6. So the number of atoms in the hexagonal closed packed layer is 6, and you just find out the volume occupied by the 6 atoms divided by the volume of the hexagon. That will give you 0.74. That means that 74% of the available volume is occupied by these atoms. So that is the maximum possible closest to packing which is available in this universe. Even if you take face-centered cubic structure, you all know that in a face-centered cubic structure there are atoms at the corners of edges, and in addition to that atoms at the edges, there are atoms at the center of each face. So the number of atoms in that face-centered cubic structure is 8 into 1 by 8, that is the corner atoms, that is 1, and 6 faces having atoms at the center of each face. So 6 into 1 by 2, that is 3. So the number of atoms in the face-centered cubic structure is 4, and 4 into 4 by 3 pi r cube, that is the volume occupied by the atoms in the face center, and divided by the volume of that cube, that is a cube. So 4 into 4 by 3 pi r cube divided by a cube, that will also give rise to 0.74. That is the packing fraction or the packing density. So that face-centered cubic structure is also having the maximum efficiency of 74%. That is, the 74% of the available volume is occupied by the atoms. In the case of face-centered, you have seen the number of atoms is 4 per unit cell, and the coordination number is once again 12, because the 4 in the same layer, 4 above that, 4 below that. So totally the number of atoms around a particular atom is 12. So that shows that any closest to packing will have the maximum of 12 nearest neighbors, which is the bottom line, which is proved once again. So to summarize the crystal structures of some important engineering materials, we started with what is closest to packing, and we have seen there are two types of closest to packings which are possible, that is square lattice pattern and hexagonal lattice pattern. And we have seen that the efficiency of hexagonal closest to packing is more efficient than the square lattice. And we have seen what are the different possible sequences in closest to packing. We have seen the sequences with n is equal to 2, n is equal to 3, and n is equal to 4. They are namely hexagonal closest to packing, face-centered cubic structure, and topos structure. And we have seen what are the rules which governs that closest to packing. For that, we have seen what is the atomic radius, what is coordination number, and what is the packing density or packing fraction. And the three important rules which governs the closest to packing are listed, and from which we have seen how the coordination number and the packing fraction plays an important role in forming the closest to packing for hexagonal closed pack structure and face-centered cubic structure. Thank you very much.